Hey everyone, today we're going to sort of do our last new thing for the electromagnetic waves unit, reflection and refraction. Kind of a tricky topic, but we'll get through it. I think we'll be okay. So, reflection and refraction are two things that happen when light hits like a boundary, which would just be like an object or like a change in medium. When light hits a change in medium, a couple of different things happen. Some of the light will reflect off of the surface. So some light undergoes a process called reflection, which is kind of just like means like it bouncing off of the surface. We'll look at more on that in a second. And some of the light does something different but sounds similar. Some of the light undergoes a process called refraction. So both of these things will happen to light when it hits a boundary. We'll start with reflection. It's a little simpler, a little bit less to it, and then we'll move on to refraction, which is a little bit more complicated. But when light hits a change in medium, again, both of these two things happen. Let's start with reflection. Again, a little bit simpler. And it's simpler because it's just light bouncing off of a surface. And actually, that's a nice way of putting it. So it's light bouncing off of a surface. And the important thing to know there is that it happens symmetrically. Meaning if it comes in at a certain angle, it'll bounce off at the exact same angle. It'll be symmetrical. This idea is what's called the law of reflection. In an equation type form, it means this. The angle of incidence is equal to the angle of reflection. Theta I equals theta R. Everything in optics we measure using angles, which is fun. And this basically says that the angle of incidence equals the angle of reflection. So theta I is the angle of incidence, and theta R is the angle of reflection. This isn't much of an equation. It just means the incoming angle is equal to the outgoing. Now, when I say angle of incidence, basically what that means is kind of just like the sciencey physics word for like incoming. So it's the incoming light, the light that approaches the boundary or the change in medium. So the incoming angle is equal to the reflected angle. What this looks like, or that symmetrical idea, would look something kind of like... And so what this would look like would be something kind of like this. You have light, like for this one we have a laser. It comes in, it hits our laser, and then it bounces out. And when I say symmetrical, like you see how this incoming angle looks roughly sort of the same as this outgoing angle? That's the law of reflection, is that those two angles are the same. This is in the reference table, that theta I equals theta R, even though it's not really much of an equation. It's here in your waves section, and it's this one right here. And again, it's just the statement that the two angles are the same, that this happens symmetrically. And this is how, like, when you think of reflections, you typically think of like a mirror, but that's exactly what happens for a mirror. So, like, if you have light from, light hits you from like the sun or the lights in the room or whatever it is, they bounce off of your body, they hit a mirror, and that light bounces off to your eye, and that's how you like perceive it or see it, is when the light hits your eye. But again, notice that we just have light, it bounces off of, this is meant to be the mirror, it just bounces off the mirror, kind of symmetrically, like this incoming angle, the same as the outgoing one, and that's reflection. But it's a little trickier than that, because we have to be sort of specific about the way we measure angles. All angles are measured from something called the normal. So this is a word we need to be familiar with. Every angle in optics is always measured from the normal. I'm going to mention this quite a few times. The word normal in math means perpendicular. So what the normal actually is, or what it means, is it's a reference line, so it's just like the line that you're measuring from, and it is perpendicular to the surface. So it's a reference line perpendicular to the surface. So I don't want to say it's like an imaginary line, because it's not, but it is where you measure all of the angles from. So let's take, our laser from before. And let's change color so you can see it. Now, if I drew a normal, so this is our mirror, and our mirror is flat, right? Flat right across the bottom. So that's our mirror. And the normal is perpendicular to it. And again, it's just this reference line that we use. So perpendicular to a flat mirror would be straight up and down. It's often drawn sort of dashed, just, because it's not actually there, so we use that. Now when I say we measure all of our angles from the normal, here's what I mean. Light comes from the laser and we're shooting it into the mirror. So we're shooting it that way. This is the normal, and so this right here is the angle of incidence, theta I. That's the angle I'm going to be referring to. So if I say the angle of incidence is like 20 degrees, then I'm saying that this right here is 20 degrees. And that angle is equal to the angle of reflection, which is also measured from the normal. So we're measuring the light ray, so we go from the light ray to the normal. So this is theta r, the angle of reflection. And it should have the same value. So like if this is 20 degrees, then this is 20 degrees. They have the same value, the angle of incidence and the angle of reflection. So it's worth mentioning that, again, always, 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 we're going to measure the angle from the normal. This angle in here is nothing. It's not a thing. It's not the angle of incidence. It's just, kind of there. This angle is also not what we're referring to. Okay? So again, always from the normal, which is perpendicular, 90 degrees to the surface, and we always measure light from that normal for everything in optics. Cool. So here's like a nice question I could ask, and this is really as tricky or as annoying as I could make it. In the diagram below, a light ray, R, strikes the boundary of air and water, causing it to reflect off of the surface. So light comes in, just like our laser from the previous picture, and it's going to bounce out like that. What is the value of the angle of reflection? And then B, sketch the reflected light. I'm going to do that first. In class, I'd have you measure this with a protractor and stuff like that, but we're not going to do that. So the reflected light would just kind of... Oh no. No. Should be a straight line like that. We're looking for something kind of symmetrical. Yeah, cool. So that's our reflected light. That's done. Great. The value of the angle of reflection. Okay, so let's start with this. I know I told you it's symmetrical, but the answer to this is not 30 degrees. It is not 30 degrees. Here's why. That 30 degrees is not from the normal. It's not from the normal to the light ray, and so it's not what we're going to use. I'm going to draw in the normal. That way we have it to refer to. Remember, it's just a line perpendicular to the surface. In this case, it's a water surface. And then there we go. That's our normal, and that's where we measure everything from. Meaning this is the angle of incidence, and this is the angle of reflection. And notice that this is not the 30 degrees that I gave you. What is its value? Well, if you remember from, whatever geometry class they do this in. If this is 90 degrees, this whole thing, this part is 30 degrees, then this part here must be 60 degrees. And if that's the angle of incidence, then the angle of reflection is also 60 degrees. And again, the thing I really want to point out here, or really want to emphasize, is that all of these angles are from the normal. They're from this, again, this line that you have to draw in, because that's just kind of what we do in physics. It's the way we measure these angles. And that's reflection. It's symmetrical, it's from the normal. And if you know those two things, you're good. On to something a little more complicated, refraction. So refraction is the bending of light when light changes medium. So when light travels from one medium to another, that light can bend or sort of change the direction that it's going in. And it has this effect of making things look sort of like distorted or almost broken, because the light that used to make this sort of like continuous type of object is very suddenly bent in a different direction. So like here's some pictures of refraction causing sort of unusual things to happen. Here we've got like a glass of water in front of the Sydney Opera House. And what you could see is that when you look at the building through the glass of water, since the light went through the air, like around the glass, and then into the glass, and then through the water, and then back into air, that's a change in medium, actually a few times, because the glass, the water, and then back to the air. And each time it changes medium, the light will bend a little bit. And that bending creates this sort of like unusual or distorted image. So here it creates this sort of like smaller one that looks a little bit bent or warped, and then here it creates this like upside down one. Again, and it's because this light bent when it changed medium. The word we have for that process is refraction. Not reflection, but refraction. You've probably seen this. I mean, this is like a really nice picture that was taken, but if you ever like put an object into like a glass of water, or like dip your hand in like a pool or something like that, it looks like it's like offset a little bit, almost like, you know, the object is like broken. Here we've got a pencil in a glass of water, and you can see like the continuous pencil, and then all of a sudden it seems like it's broken. Like the second half is not connected to the top half, and that's because of refraction. The light is traveling from the pencil through the water, and when it hits the air, it changes medium from, you know, water into air. And when it does that, it bends a little bit. So the light that looked like it was, you know, over here is now over here, and you sort of perceive it as being off. So like, you know better, you know that the pencil's not broken, but the light sort of fools your eye into seeing this, because again, it bent, it changed where it looked like it was. Here we've got this guy, it looks like his head is taken off, because again, we've got light traveling, you know, and the top half is where he actually is. The light goes straight from his head to where the camera is. It doesn't change medium. The light's in air the whole time. But for his bottom half, that light, it goes through the water, and then through whatever this glass is, and then into the air, and when it changes medium, it bends. That's refraction. So it creates these sort of broken images because the light bends. It doesn't travel a straight path. It changes its direction when it changes medium. What causes this? Well, it's caused by a change in the light's speed. So when the light changes how fast it's moving, that's what causes this bending to occur. Kind of what happens is like a part of the light beam will change speed before a different part of the light beam, and that causes it to sort of like wheel around and change its direction. In class, we'd really dive into this, but I don't know, for this format, I think we can just settle for this. So it's caused by a change in the light's speed is what creates this bending effect. So we're going to kind of skip some of this, because again, in class, we'd really go crazy with this. And let's actually just do 10. We're going to sort of skip through these guys. So, laser beam is directed at the surface of a smooth, calm pond, as represented in the diagram. Which organisms could be illuminated by the laser light? So we shoot light at a surface. And which of these things would get hit? Well, a couple of different things happen when the laser hits this new surface. Some of the light, like we said earlier, will reflect and bounce off towards the bird. So this bird would get hit by part of the laser because some of the light reflects. Notice we have this normal that we always use to measure angles, and the angle of incidence is equal to the angle of reflection. Now, some of the light, though, will go through and into the water, because water, you know, it's transparent. Light can travel through it. But, so the bird will definitely get illuminated. Let's circle it. Now, but that light, when it changes medium, will not travel straight and hit the seaweed. What happens is the light, when it enters this new medium, will actually bend a little bit and change direction. So the direction it'll actually travel in is this way, and it'll hit the fish. So, and again, notice that the light doesn't travel straight, it kind of bends a little bit. That's that refraction, so it won't follow that straight path. It's worth pointing out the crab will not get illuminated because the light doesn't bounce off of the normal. The normal is not like a physical thing. Remember, it's just the line that we use for reference. What this actually looks like if you were to shoot this laser is you'd end up with something that looks kind of like this, and this is kind of a nice picture that's got everything sort of in it. You shoot this laser at a glass block, and when you do that, light is changing medium. It goes again from air into glass is what you have here. The light comes in, and when it does that, two things happen. Some of the light reflects and bounces off, and some of the light refracts. And notice that it looks like it's like bent a little bit, like it didn't follow like an exactly straight path as it went from air into the glass. That's refraction. So some light bounces off, and some light will bend. And then actually you've got sort of a continuing pattern of reflection and refraction as you follow this. The light reflects off the bottom. Again, notice this symmetrical thing right here. That's that bouncing off of the interface. And then back up here, notice that the light comes in, and see how it like bends outwards a little bit, like it bent. That's refraction again, when the light changes medium. So reflection occurs and refraction occurs, both of these two things. Here we've got it again. Light comes in, and it's sort of like very nice and clearly shown. If it went straight, it would travel, again, like directly across, but it doesn't. It looks like it bends at this interface, and then it bends one more time at the end. So that's our refraction, is when light changes medium, it'll bend. But we got to be a little more specific. We have to be able to do the math for it. And most of the questions I ask you for this topic will deal with the math. The equation that describes refraction is Snell's law. And basically it's this. N1 sine theta 1 is equal to N2 sine theta 2. It's a weird equation. We're going to go over how to use it in a second, because it's not going to be super obvious at first. But first, let's write out what everything means. So, N1 and N2. N1 and N2 stand for the index of refraction, which was covered in one of the previous videos. Index of refraction, it's like a measure of how much a material slows down light, because remember, this has to do with a change in speed. And it's the index of refraction for two materials. Since this happens when light changes medium, it'll be like material number 1 and material number 2. So you've got the index of each of the two materials. Sine is just sine, like in your calculator. Make sure you're in degree mode. And then theta 1 and then theta 2 stand for the angles of incidence and the angle of refraction. So the angles of incidence and refraction. These are our two angles here. So we've got material number 1, material number 2. So N1 and N2 stand for the index of the first material and the second material, and then theta 1 and theta 2 stand for the angles of the two materials. Let's kind of look at what this would be if we did one of those pictures. So let's start by taking this picture right here, which again is light bending or refracting when it enters the glass, and then one more time when it leaves the glass. Let's rotate it so that the glass is like perfectly flat like this. Now, if we're going to use this equation, which we're not going to solve the whole thing, but let's go over like what all the different variables and stuff like that would mean. First thing I'm going to do is I'm going to put in a normal, which is this perpendicular line. So let's do the refraction for like this bending right here when the light comes in and then it bends and goes this way. Let's get rid of those because they're sloppy. Okay, so if this were a problem, every time we talk about refraction, there's an equation that we're going to use, and it's going to be the same equation. We're going to do this equation kind of a lot. N1 sine theta 1 equals N2 sine theta 2. Okay, so the way you use this equation is kind of like this. What we're going to do is you can choose the first material to be material number 1. So what I mean by that is, like, let's use this material over here, like what the light is in over here. And it's not moving through the glass, I think it's traveling through the air, right? So this is air up here, and this is glass down here. Okay, so N1 would be the index of air. So the reason you would know that, or know what to plug in there, is you are going to have to go to your reference tables, which I've got open right here. Air has an index of 1. So if we were plugging into this equation, N1 equals 1, because it's the index of air, the first material. Angle 1, well, angle 1 would be the angle in the air, which is this right here, whatever it might be. So let's be a little more clear. This would be angle 1. I'd have to give that to you in the problem. Okay, and then all of these things on this side, with the 2 subscript, all of those are going to be material number 2, which for this one I think is the glass. So angle 2 would be the angle of refraction, which is in the glass. So I think it's this angle right here, theta 2. For both of those angles, notice how I did them from the normal, from this dotted line to the light, from the dotted line to the light. Always, always, always when we do light, we measure from the normal. And then N2 would be the index of glass. I'd have to be specific. You actually have a couple types of glass here, so let's call it flint glass. I don't know what the difference is really between the types of glass. So we would say like N2 is equal to 1.66. I'll either give that to you or ask you to look it up in the reference table. And this is, an equation that you can do. You are going to need a scientific notation calculator. If you really need one, one that I recommend is online. You can go to desmos.com. It's this right here, desmos.com. And if you click the scientific button, it's got a pretty good calculator. It's got like the functions. It's in degree mode. You can kind of type in, and it's one that I think is easy to use. That in mind, let's try a question. We'll see how it goes. Here we go. So here's a good, full of reasons question here. Array of monochromatic light with a frequency of 5.09 times 10 to the 14 hertz passes from air into lucite at an angle of incidence of 30 degrees. So they're always going to give you this same frequency because it's the frequency that matches your reference tables. This 5.09, this 5.09. It's not going to affect our problem at all, so we're just going to kind of look right past it. Passes from air into lucite at an angle of 30 degrees. Calculate the angle of refraction in the lucite. Okay. So, anytime we're doing this refraction stuff, it's going to be Snell's law. N1 sine theta 1 equals N2 sine theta 2. Again, like every time it's this physical thing, this is the equation. So you'll kind of always know exactly like where to look, I guess you could say. Okay, material number 1 is going to be air, so this will be material 1. Material number 2 is going to be lucite. So everything with this 1 subscript is going to be in the air. So N1 is the index of air. Theta 1 is the angle in the air. So let's go. N1 is the index of air. Why would you know that? Because it's right here in the reference table. It has a value of 1. 1. It's unitless, that index of refraction, so I'm not going to plug anything in there. Theta 1 is the angle in the air, which it looks like is this 30 degrees. Notice it's measured from the normal, which is good. Times sine of 30 degrees. That says 30. There we go. Cool. N2 is the index of material 2, which is lucite. It's like a type of plastic. Lucite, it looks like, has a value of 1.5. So I'm going to plug in 1.5 as N2 times sine of theta 2. I'm going to show all of my work here. This is kind of a tricky sort of thing, so I'm actually just going to make this all kind of... There we go, because I want to go right through it. Okay, so math-wise, here's what you have to do. We are going, again, we're solving for that theta 2. So the first thing I'm going to do here is I'm going to divide both sides by... actually, you know what I'm going to do before that? I'm going to plug in 1 times sine of 30. Oops, that's back. That's okay. 1 times sine of 30. Basically, I'm going to plug in this left-hand side of the equation. 1 times sine of 30, if you do that in a calculator, is... Again, make sure you're in degree mode or you get the wrong thing. 1 times sine of 30 should be 0.5. There we go. So we've got 0.5 is equal to 1.5 times sine of theta. Okay, next thing I'm going to do is I'm going to get rid of the 1.5. So I'm going to divide both sides by 1.5, and then I'm going to divide this side by 1.5. 5 over 1.5 is, I think, 0.33, like 0.3 repeating. So 0.333 is equal to sine of theta. And now, here's the tricky part. You probably haven't done this one in a while in your math classes. We're solving for this angle right here, which means we need to get rid of sine. And the way you do that is you do arc sine or inverse sine. Some of you call it second sine because that's what you type in your calculator. It's the thing that looks like this in your calculator. Let's see if I can pull it up on TI-84. So if you have one of the calculators, like one of these, the TI-84s, it's you hit second right here, and then you hit sine, and you see the sine to the -1? That's what you want to do. And basically what that does is it undoes sine. It's the inverse function of sine. So I'm going to do, let's change color for that. I'm going to do sine -1 of 0.33. And again, when you do sine -1 of this side, that cancels out. Inverse sine of 0.33 is, and this is part of why I like this thing, because it's got, if you hit this function, it'll have that for you. So again, we're doing the inverse sine of 0.333, and you get about 19.46. So theta 2 equals 19.46 degrees, because it's an angle. And that's it. That's our angle of refraction. So when it says to sketch the refracted light, basically what it's going to do is it's going to look like this. Oops. And this angle in here is that 19.46. And there we go. So these problems are a little mathematically sort of weird. It's just like a strange equation. But that's our idea. So we're going to do 12 and 13. I want you to try both of them. So try number 12. I'm going to go over in a minute. And then try number 13, which I will also be going over. Alright, so for number 12, hopefully you paused it and tried it. Alright, a ray of light is incident. Notice I gave you that same frequency. Not really going to affect us, but it's there. Is incident on the boundary between air and an unknown material x at an angle of incidence of 55 degrees. So we got that angle of incidence here. As shown, the absolute index of refraction of the material is 1.66. Okay, so when the light hits this change of material, it's going to bend. It's not going to travel straight. It's going to bend. So let's see what we can do. We want the speed of light in material x. That's a v, right? Speed. We know the index of this material, so this one kind of isn't going to be the Snell's law equation that we were just doing. It is going to be, if we're talking about speed of light, this is the equation for the speed of light in different materials. N equals c over v, kind of from one of the previous videos. So N equals c over v. That index is 1.66 for N. C is always in an equation. 3 times 10 to the 8th meters per second over v, which is what we're solving for. Cross multiply carefully. And I got a velocity of, you probably got a really big number, because light's still really fast, even though it's a little slower in this material. I got oh, yikes. I got 1.12 times 10 to the 8th meters per second. It's okay if you didn't write it in scientific notation. If you didn't, it was like 12 million something. So again, 1.12 times 10 to the 8th meters per second. Cool. Now we want the angle of refraction. So we're doing the angles, we're doing refraction. As soon as you see that, n1 sine theta 1 equals n2 sine theta 2. And I am going to go slow and go through all the math, because it's kind of like a weird equation for that. So if you're good with the math, you can kind of skip to the end, but for now, let's do this. Alright, air is going to be material 1. Material x is going to be number 2. So everything on the left-hand side with these 1 subscripts is going to be in the air. So n1 is the index of air. Why would you know the index of refraction of air? Well, it's in your reference table. It has a value of 1. So, 1 times, oh, I got a virus, times sine of 55 degrees equals n2 is, I think, the other material, which I told you its index. It's 1.66. So, equals 1.66. Let's maybe make that actually show up. 1.66 times sine of theta. Okay, this is a good setup. This is a degree symbol right here. If this is a good setup, let's start doing the math. I'm going to start with 1 times sine of 55. So, 1 times sine of 55 is, got 0.819. I'm going to try not to round too much. I'm going to go with 0.81915. Let's go with 0.81915 is equal to 1.66 times sine of theta 2. Alright, again, we're solving for that angle, so the first thing we'll do is get rid of the 1.66. I'm going to do that by dividing. Divide by 1.66, divided by 1.66. Over here, okay, so we're going to take that 0.81915 and divide it by 1.66, which gives us 0.4935, let's call it. 0.4935 is equal to sine of theta 2. Okay, now we have to get to that angle, because we don't want sine of the angle, we want the angle. And what we do about that is that inverse sine function, which again, if you have one of these, is second sine. For this guy, hit this function button, inverse sine of, can I just copy and paste that? Is that going to work for me? There we go. And that's it, 29.57, let's call it. So theta 2 equals 29.57 degrees, our angle of refraction. So that means that's this angle right here, about 29 degrees. Cool. That's it. Alright, try 13 on your own. So pause the video, give this one a shot, but I'm going to go over it in a minute. Okay. I hope you tried it. Array of monochromatic light with, okay, notice I keep giving you the same frequency, is incident on an interface of air and corn oil. So remember, air has that index of 1, n equals 1. And corn oil. So for corn oil, n equals 1.47. This trends at an angle of 35 degrees. So this is our 35 degrees. Cool. And then is reflected from the surface of a plane mirror located below and parallel to the glycerol layer. The ray emerges from the corn oil back into the air point P. So basically, they're just kind of describing the diagram. Let's go. Find the angle of refraction of light as it enters corn oil from the air. So notice we don't go straight here. It kind of bends a little bit. We have this angle of refraction, which we're going to solve for. And again, it's the equation that describes this thing is n1 sine theta 1 equals n2 sine theta 2. So if you're, once you see that it's this refraction idea with the angles and the indices of refraction, this is the thing we do. Material 1 is going to be air, which has an index of 1. So 1 times sine of theta 1. Okay, that's the angle in the air, in the first material. So times sine of 35 degrees. 35 degrees. Cool. Awesome. Equals N2, which is the second index. So in this one, I think it's the corn oil, because that's what we're solving it in. So equals 1.47 times sine of theta 2. And again, I'm going to walk through the math kind of slowly here. Alright, 1 times sine of 35 is, so again, make sure you're in degree mode. Let's start a new line. So we're doing 1 times sine of 35 degrees. I got 0.57358. Let's go with that. 0.57358 is equal to 1.47 times sine theta. Okay. And the next thing we're going to do is, again, we have to get rid of the 1.47 first. So I'm going to divide both sides by 1.47. Do it to the right-hand side. Do it to the left-hand side. So I'm going to take my answer, which is, hit this and there we go. Just hit A and S, and it pops up your answer. We're going to divide it by 1.47. And I got 0.390188. Let's go with the whole thing. 0.390188. 88 is equal to sine theta 2. And again, that last step you have to do, like this is not, okay, we're not done, is the inverse sine function, which basically gets rid of this. But if you do it to one side, you have to do it to the other side. So we're going to do the inverse sine of this answer right here, which is, if you click this, it'll plug it right in for you. Alright, I got 22.966 degrees. Let's go with that. 22.966 degrees equals theta 2. And there we go, refraction. So again, one of the trickier things that we do this year, that we're going to do online. So, yeah, if you have any questions, let me know or stop by my office hours.